Hi, everybody. In this video, we're going to go over Regents Review number 3. This one had a lot of proofs. The whole Regents Review was proofs, so it was a bit difficult. So we're going to go through all of the questions together. So in the first question from the Regents Review, we're told that PQRS is a parallelogram. I know a lot of things about parallelograms. I know that opposite sides are congruent. I know opposite angles are congruent. I know opposite sides are parallel. Those are just some of the things I know about parallelograms. So I'm going to keep all of that in mind. I also know that QT is perpendicular to PS. So that means where they intersect, they make a 90-degree angle. And I also know that SU is perpendicular to QR. So I know that where they meet, a 90-degree angle is formed as well. We need to prove PT congruent to RU. PT is a side of this triangle over here that I'm highlighting in yellow, and RU is a side of this triangle over here that I'm also highlighting in yellow. So if I want to prove that corresponding sides of two triangles are congruent, my first step is going to be to prove the triangles themselves congruent. Then, after I know for sure that the triangles are congruent to each other, then I can use CPC to say that all of the other corresponding sides or angles, but here we're talking about sides, are also congruent. So step one, prove the two triangles congruent. Step two, use CPCTC to prove the proof statement. So we know that PQRS, the whole big quadrilateral over here, is a parallelogram. So one thing I know about parallelograms that would also help me with these two triangles is that opposite sides are congruent to each other. I also know that opposite angles are congruent to each other. And there I have enough information to prove the two triangles congruent. I have the two triangles congruent by angle, angle, side, angle, angle, side, or AAS for short. Once I prove the triangle is congruent with AAS, then it's one more step in my proof to prove corresponding sides PT and RU congruent using CPCTC. I'm going to pause the video and write up the proof. You should do the same thing and try to write up the proof by yourself if you didn't already for Regents Review number 3. That way you make sure that you're able to take everything that we just discussed in the proof and transfer it into your two-column statement reason chart. Please take a minute and read through the proof and just see that everything that's marked in the diagram is in the proof. We have the right angles. You do need to state both how you know that these are right angles and that they're congruent. So I just did that in one step, and that gives us our first pair of congruent angles. Our second pair of congruent angles comes from the opposite angles in the parallelogram. And oops, and our side comes from the opposite sides of the parallelogram. So that's our side. So here we have AAS. Okay, moving along. Over here, I have part 1 of the coordinate proof. AB and BC are congruent, so triangle ABC is isosceles. I use the distance formula to show that. Make sure that when you're doing a coordinate proof, for each question that you're answering, you show all of your work, and then you put a concluding statement explaining in words what your work shows. So I have a sentence here explaining what my work shows. Now for part 2, we need to show that ABCD is a square. We need to find the last point that makes it a square. So I'm going to use slopes to do that. So I'm going to count from point A to B, just from any 2 points. So that is, oops, up 1, 1, 2, 3, 4, 5, 6 to the left. So up 1, 6 to the left, that's a slope of -1/6. So I know that in a square, since squares have 90-degree angles, any two sides next to each other form a right angle, so they're perpendicular. And we know that perpendicular lines have opposite reciprocal or negative reciprocal slopes. So I know the slope from point A to point D, wherever it is, somewhere over here, should be the opposite reciprocal because it's going to be the side right next to this one. So it's going to form a 90-degree angle with it. So the opposite reciprocal slope of -1/6 is 6/1. Now, if I go up 6 and over 1, I'm going to be like somewhere over here. So I'm just going to do the reverse. I'm going to go down 6, 1, 2, 3, 4, 5, 6, and right 1. And that should be the point D that I'm looking for to make my square. Okay, I connected that really terribly. Let me try that again. Okay, that's as good as it's going to get connected. That is the point 1, 2, 1, 2, 3, 4. So that's 2, -4. And all that the question is asking here is for us to state the coordinates of that point. The last part of this question is actually a very long part. It's to prove that this is a square. So we need to do a couple of things before we can prove it's a square. Before something can be a square, it first needs to be a parallelogram. So we need to prove it's a parallelogram. Then we need to prove it's a rhombus and a rectangle. And then we'll know for sure that it's a square. So there are 3 steps involved in proving that it's a square. We have to prove parallelogram, rhombus, and rectangle. Since I already, in part 1, found the lengths of 2 of the sides, AB and BC, I'm just going to find the lengths of the other 2 sides, CD and AD, because I already have 2 distance formulas done already. And when I was plotting my point, I moved to the right instead of the left, so I accidentally wrote down the wrong point. So I'm going to change that real quickly. That looked a bit off. So let me edit that. You were probably watching and wondering where that point came from. That was my mistake there. So that is 0, -4. So I just need to edit my distance formula slightly. And I see here that all of the lengths of all 4 of my sides are all the same. They are all radical 37. So I'm just going to put a concluding statement that explains what my calculations show so far. So let me write this really, really small. Quadrilateral ABCD is a parallelogram because both pairs of opposite sides are congruent. That's what I showed with my distance formulas by showing that all 4 sides were equal. Okay, so now I need to prove a rhombus property and a rectangle property. Remember, one property of a rhombus is that consecutive sides are equal, which means all the sides are equal. A rhombus is equilateral. So I'm going to write here, ABCD is also a rhombus because it is an equilateral parallelogram. Okay. And then I just need to prove that it's also a rectangle to be a square, because remember, to be a square, it needs to be a parallelogram, a rhombus, and a rectangle. So I can do that with slopes. We already talked about how rectangles have 90-degree angles. So any 2 sides next to each other should be perpendicular. So if I count from this point to this point, I'm going up 1, 2, 3, 4, 5, 6, and right 1. So as we said before, that's a slope of 6/1. And we already counted from this point to this point, and it was -1/6. So we do have opposite reciprocal slopes, meaning that the 2 sides next to each other are perpendicular, so they form a right angle. So I'm going to write that down in a concluding statement. Let me add on to what I have here. Since the slope of BD is -1/6 and the slope of that was BA. My bad. I wrote on it so it looked like a D, but that was an A. And the slope of BD is 6. the sides are perpendicular, so they form a right angle. A parallelogram with right angles is a rectangle. And then I'm going to finish this up by explaining why it's a square. ABCD is a square because it is both a rhombus and a rectangle. By definition, a quadrilateral that is both a rhombus and a rectangle is a square. So this did have a lot of components. You did need to show that it was a parallelogram, a rhombus, and a rectangle before it could be a square. Taking a look at the next proof over here, what we are given is that triangle ABE and triangle CBD are congruent to each other. Now, those triangles are the larger triangles here and they're overlapping, so I can't really see what belongs to them very well. So, whenever I'm working with overlapping triangles, a good idea is to take the two triangles and to just draw them separately somewhere else on your paper. So, this was A, B, E, one of those congruent triangles, and this one was C, B, D, the other congruent triangle. Our goal is to prove that the small triangle, AFD, is congruent to this other small triangle, CFE. So basically, since we know that the two red triangles, the two larger triangles, are congruent, we want to try to use CPCTC to get some more information about the smaller triangles. Because since these triangles are congruent, we know that all the corresponding sides and angles are automatically also congruent by CPCTC. Because in congruent triangles, everything is congruent if you already know that they're congruent. So if we can use that to get more information about these triangles, that's also part of these triangles, then we can get what we need to prove these two triangles congruent. Before we get started with that, I already see vertical angles. So that's one pair of angles that we can definitely use to prove the triangles congruent to each other. Now, it would be really helpful if we could get side AD and side EC. BC is the side of this bigger red triangle. AB is the side of this bigger red triangle. So we know that they're congruent to each other. What we need to do is get rid of BE and get rid of DB. If we subtract off BE from BC, we'll be left over with EC, which is what we want. If we subtract off BD from AB, we'll be left over with AD, which is what we want. Now, DB is a side of this red triangle, and BE is a side of this red triangle, which are congruent. So we know that BE and DB are congruent by CPCTC. So we can subtract here because we're starting with two long congruent segments, and we're subtracting off two segments that we also know are congruent. So we'll be left over with congruent segments AD and EC. So that will give us another side that we can use to prove the triangle's congruent. So we just need one more thing. We either need another angle or another side. Now, the angle is going to be the one easier to get because if you know this, angle A is inside this small blue triangle, but it's also a full angle in this triangle. And angle C is in the small blue triangle, but it's also a full angle in this triangle. So we already know angle A and angle C are congruent to each other as well because of CPCTC, because the two larger triangles that also have angle A and angle C as part of them are already congruent. So these have to be congruent by CPCTC. So that's why drawing triangles separately is very important. It helps you see what belongs to each triangle clearly. Otherwise, it would have been really hard to tell that angle A and angle C were part of those triangles and that we could say that they're congruent to each other by CPCTC. I'm going to take a second and write down the proof. You should pause the video and try to write the proof down yourself if you didn't have this idea. We see ultimately we're going to be proving these triangles congruent by AAS. AAS is what we have here in the two small blue triangles. Here is the full written up proof for this question. Notice that everything needed for AAS is in this proof. I started off with the vertical angles. So that's right over here in step 2. So that's 1A that we were using for AAS. And then through subtraction, we were getting AD congruent to EC. So I just fully wrote out my subtraction. Before I can subtract, I do need to know that the pieces I'm starting with, AB and BC, are congruent. So that's in my proof. AB is congruent to BC due to CPCTC because they were parts of the triangles that we originally knew were congruent to begin with. I need to know that the pieces I'm subtracting are congruent. That way my differences stay congruent. So that's DB and BE. So that's in my proof before the subtraction as well. DB is congruent to BE due to CPCTC because they were also sides of the triangles that we originally knew were congruent from the givens. So now that we know that we're starting with congruent segments and subtracting congruent segments, we know that our differences, what's left over, which would be AD and EC, that was the goal of our subtraction, that's what we're being left over with, are congruent as well. So when I'm actually doing the subtraction, that's my subtraction postulate. I'm replacing AB minus DB with what it actually is. When you do AB, take away DB, you're left over with AD. You're substituting this for what it is. When you do BC minus BE, you're left with EC. So I'm substituting this for what it actually is. After my subtraction, I have, and that's my S, AD congruent to EC is the S that I'm using. And then I just need my last A for AAS, and that's angle A congruent to angle C. And that's by CPCTC because those were also angles in the triangles that I originally knew were congruent. So here I have everything I need for AAS. Okay, moving on to the next one, and this one's a little simpler. So I'm taking a look over here, and we have angle ABG congruent to angle CDG. We have AB congruent to CD. And we had CE congruent to AF. Our goal is to prove that FG is congruent to EG. So FG is a side of this triangle here, and EG is a side of this triangle here. So I can already see that my goal is that I'm going to be proving these two triangles congruent. And then after I prove these two triangles congruent, I can use CPCTC to prove that the corresponding sides of them, FG and EG, are also congruent. Prove the triangle's congruent, then use CPCTC. Let's talk about how we're going to do that. So the first thing I realize is not only do we have this pair of opposite sides congruent to each other, but I also know that these angles are congruent. Now those angles, and I'll just make my Z for a second so you can see, are alternate interior angles. And we know that when we have congruent alternate interior angles, that proves that the lines that form them are parallel to each other. The lines forming that Z are parallel. So what I have here is I have in my quadrilateral ABCD, I have one pair of opposite sides that is both congruent and parallel. And that proves that ABCD is a parallelogram. Now that I know ABCD is a parallelogram, I know that all of my parallelogram properties apply. So I know that opposite sides are congruent to each other. And if I know that BC is congruent to AD, if I'm starting with congruent segments, and I know that AF and EC are congruent from the givens, I can start with congruent and subtract congruent to be left over with congruent. Here as well, I can start with congruent and subtract congruent to be left over with congruent. I also have my congruent vertical angles. And I also know, since ABCD is a parallelogram, that the opposite sides are not only congruent, but they're parallel. And once I know that these opposite sides are parallel, I know that the alternate interior angles formed by those parallel lines are also congruent. So I see here that I have AAS. There's been a lot of AAS in this Regents review. Now, this is a lot of stuff to put in the proof. So please pause the video and try to write it up. I'm going to do the same thing so you can see what it looks like. This proof is quite long. It took me 11 steps to write it up. So after my givens, I mentioned that AB was parallel to CD. And once again, the reason I knew that was because we were given those congruent alternate interior angles. Now, I know that ABCD is a parallelogram because, once again, if one pair of opposite sides is both congruent and parallel, then the quadrilateral is a parallelogram. And once I know I have a parallelogram, I know that the opposite sides BC and AD are congruent. That's my step number 4. So then, since I'm starting with congruent segments BC and AD, I subtracted off EC and AF to be left over with BE and FD. Remember, as long as you start with congruent and subtract congruent, your differences will be congruent. BC minus EC is BE through substitution. AD minus AF is FD. So we're replacing this with what it actually is. That's substitution. So that gives me my first S. Let me write that in here for my AAS. My only S that I need actually for AAS. So that's these sides of the 2 yellow triangles. Then I mentioned the vertical angles. So we know that intersecting lines form congruent vertical angles. Make sure you mention your vertical angles with 3-letter names. It's not angle G congruent to angle G. It's not reflexive property. They're vertical angles. And then I need to get my last pair of angles, which are these alternate interior angles. But before I can mention them, I do need to say that the lines forming them are parallel. So I said that BC is parallel to AD in my next step. And my reason for that is opposite sides of a parallelogram are parallel. And then I can say that my alternate interior angles are congruent because we have those parallel lines cut by a transversal. So here was an A, my vertical angles, and then those alternate interior angles were the other A that I need for AAS. And so I have everything I need for AAS. So I said that the triangles were congruent by AAS. And then it was one more step to prove the proof statement using CPCTC. Because once we know the triangles are congruent, their corresponding sides are also congruent due to CPCTC. And that's the whole proof.